Hello. In the previous lecture, we discussed Euclid's algorithm and how it can help us to compute the greatest common divisor of two integers in an effective way. We have also seen some of the basic properties of the greatest common divisor of two integers. Today, we are going to investigate, in this lecture, we are going to investigate elements of the ring of integers modulo n that have multiplicative inverse. So let's start with the definition of multiplicative inverse. So let's start with a residue class A mod n. We say this residue class has a multiplicative inverse if this residue class times another one ends up being the neutral element of z sub n with respect to multiplication. And the neutral element of z sub n with respect to multiplication is the residue class of 1. So if there is a residue class A prime, so that residue class of A times residue class of A prime ends up being the residue class of 1, we say the residue class of A has a multiplicative inverse. Alternatively, we say residue class of A is a unit of the ring of integers modulo n. Later in 103, in the next course, when you learn about ring theory, a system of numbers with addition and multiplication will be called a ring. That's why I called it ring of integers modulo n. But in any case, if an element of z sub n has a multiplicative inverse in this sense, we also call it a unit. The set of all the units of z sub n is denoted by z sub n sub cross. Cross is supposed to remind us that it has a multiplicative inverse. Now, the next theorem gives us a complete understanding of the set of all the units of the ring of integers modulo n. So what are they? Assuming that n is an integer that's at least 2, the ring of units, the units of integers modulo n consists of the residue classes, bracket A, square bracket A, where A is co-prime with n. So it consists of residue classes A, where the GCD of A and n is 1. Moreover, we can say how many elements in the ring of integers modulo n are units. That number is precisely the so-called Euler's phi function, which is the number of integers from 1 to n that are co-prime with n. So where GCD of A and n is 1 and A is ranging from 1 to n. It is interesting and important to include both 1 and n, even though when n is at least 2, then we cannot have A to be equal to n and the GCD 1, but this definition is consistent with the case when n is 1 as well. So phi of 1 by definition is supposed to be 1, which is the same as saying, which is consistent with this definition. Okay, so that's the theorem that we want to discuss. As always, when we want to show equality of two sets, here we want to show that the set of units of the ring of integers modulo n is the same as the residue classes where the representative is co-prime with n. I want to show that these two sets are equal. We are going to discuss why the left-hand side is a subset of the right-hand side and why the right-hand side is a subset of the left-hand side. Okay, so suppose I give you a residue class and I tell you that it is a unit. So that means I'm giving you this residue class, I'm telling you that it is a unit. What does that mean? This means that this residue class times some other residue class that we don't know what it is ends up being the residue class represented by 1. Now, by definition, product of these two residue classes is the residue class that's represented by the product of these two integers A and A prime. So that means some representative that's a multiple of A can represent the residue class of 1. That means that a times a prime is congruent to 1 modulo n. A times a prime is congruent to 1 modulo n. These two residue classes are equal if and only if these two representatives are congruent modulo n. Now, we've seen this when we wanted to prove Euclid's algorithm. We've seen that if B is congruent to B prime modulo n, then GCD of B and n is the same as GCD of B prime and n. Now we know AA prime is congruent to 1 modulo n, and therefore GCD of AA prime and n is the same as GCD of 1 and n. Okay, so GCD of AA prime and n is the same as GCD of 1 and n, but GCD of 1 and any other integer is 1. So that means A times A prime and n are co-prime. They have nothing, no multiplicative factor in common. Of course, then that would imply that GCD of A and n should also be 1. They cannot have anything in common. That's one way of arguing, but alternatively, this is how you argue. You say when GCD of A and AA prime and n is 1, then that implies that an integer linear combination of them should be 1. But from here, I deduce that some integer linear combination of A and n is 1, from which we deduce that GCD of A and n is 1. So in either way, because GCD of A prime and n is 1, we can deduce that GCD of A and n is 1. Alternatively, we can say that if D divides both an A and n, then D divides AA prime and n. Therefore, knowing that GCD of AA prime and n is 1, we can deduce that GCD of A and n should be 1. In any case, we proved that if A is, if the residue class of A is a unit in the set of integers modulo n, then GCD of A and n is 1. Now I want to show the other way around. I want to start with a residue class that's represented by an integer that is co-prime with n, and I want to show that this residue class is a unit. Okay, so let's start with an integer a, assume that GCD of A and n is 1, from which we deduce that an integer linear combination of A and n should be 1. So 1 is an integer linear combination of A and n. Okay. Now let's look at this equality modulo n. Knowing that Ra plus some multiple of n is 1, we deduce that Ra is 1 modulo n, because this part is a multiple of n. That means Ra minus 1 is a multiple of n. Therefore, Ra is 1 modulo n. Now, this congruence relation implies that the residue class represented by Ra modulo n is the same as the residue class that 1 represents modulo n. And now, by definition of product of residue classes modulo n, we deduce that the residue class of R mod n times residue class of A mod n is residue class of 1 mod n. That means this residue class is a unit in integers mod n. That's exactly we wanted to show. That there is a cross over here, it's missing. That implies that this is a unit in integers mod n. That's exactly what we wanted to show. Okay, now this implies that the first part implies that the left-hand side is a subset of the right-hand side, and now we showed the other way around, and therefore we get equality. Now, I want to say that I don't need all the integers that are co-prime with n and the residue classes that they represent in order to get the set of integers, the units that are units of the integers modulo n. I only need to focus on the integers that are in the interval 1 to n. So my claim is that the residue classes that are represented by integers in this interval and co-prime with n are giving me the entire set of units in integers modulo n. Of course, we have already discussed that if a residue class is represented by A and N are co-prime, then this residue class is a unit in integers modulo n. Therefore, we do have this inclusion. The whole point is to show the other way around. So we start with a unit inside integers modulo n, and I want to say that it can be represented by some integer in this range and co-prime with n. Okay, but we know that every unit that I give you is of the form some residue class of an integer b, where GCD of b and n is 1. Here I forgot to write down equals to 1. Now notice that if I take the remainder of b divided by n, this remainder by definition is in this range. And by definition of long division, b is n times some natural number, integer number that we call quotient, plus the remainder r. Because of this equality, we deduce that b is congruent to r modulo n, and therefore GCD of b and n is the same as GCD of r and n. But remember, because we started with some units here, we knew that GCD of b and n is 1, and therefore GCD of r and n is 1. Altogether, we end up showing that the residue class that's represented by b is equal to the residue class that's represented by r, the remainder, and moreover, this remainder is co-prime with n, and furthermore, because we assumed n is at least 2, and r is the remainder, so r cannot be 0, because GCD of 0 and every other integer would be that integer. Every other non-zero integer would be that integer, but n is at least 2, so r cannot be 0. So altogether, we get some integer r that is ranging from 1 and strictly less than n, and it's co-prime with n, and the residue class of r modulo n is the same as the residue class of b modulo n, and that was an arbitrary unit in integers modulo n. Altogether, we show that every unit in integers modulo n is of this form. It's residue class of some integer in this range and co-prime with n. That completes the proof. That shows that every integer in this range, in particular, the cardinality of the units modulo n is equal to the Euler phi function of n. Okay, let's see an example or two. Let's say list all the elements in z sub 6 cross. That means we want to find all the units in z sub 6. We proved that units of z sub n cross consists of residue classes that are represented by integers from 1 to n, and GCD of a and n are supposed to be 1. In this case, n is 6. So this means that we are looking at the we are looking at the residue classes that are represented by a, where a is an integer from 1 to 6, and GCD of a and 6 is 1. Okay, but in this range, the only integers that are co-prime with 6 are 1 and 5. 2 is even, 3 divides 6, 4 is even, and 6 is also even. and 5 and 6 are co-prime. So that these are the only elements that are units modulo 6. Now let's list all the elements in Z sub 8 cross. Again, by the same theorem, Z sub 8 cross consists of residue classes that are represented by elements, by integers, in the interval 1 to 8, and GCD of A and 8 is supposed to be 1. Now notice, all the elements of 8, what are the elements? Divisors, not elements, all the divisors of 8, what are those? They are 1, 2, 4, and 8. Except one, the other divisors, 2, 4, and 8, all of them are even. That means GCD of A and 8, if it's not 1, then it should be even. Okay, so that means what? That means if I start with an integer that's not even, then it should be co-prime with 8. So every odd number is co-prime with 8. And vice versa, if it is even, of course, they have 2 in common with 8, therefore they cannot be co-prime. So altogether, we deduce that A, GCD of A and 8 is 1 if and only if A is odd. So if A is odd, then GCD is 1, because every other divisor besides 1 of 8 is even, and vice versa. If A is not odd, then it has 2 as a factor and 8 has a 2 as a factor, then the greatest common divisor is at least 2. So and that's exactly what I have over here. Altogether, we get that GCD of A and 8 is 1 if and only if A is odd, and therefore the set of units of integers modulo 8 consists of residue classes that are represented by odd numbers from 1 to 8. That means residue class of 1, residue class of 3, residue class of 5, and residue class of 7. In particular, there are 4 of them. By the same argument, we can understand primes, residue classes modulo primes, or residue classes modulo powers of primes. Let's start with residue classes modulo a prime number, because that's important. It plays an important role later in this course as well. So let's start with that. So suppose P is a prime number, and I want to understand the set of units of integers modulo P. And interesting thing is that here, every non-zero residue class has a multiplicative inverse. It has a similarity with rational numbers. It has a similarity with real numbers. Every non-zero element in this set has a multiplicative inverse. It is not similar to set of integers where all the integers except -1 and 1 do not have multiplicative inverse. But here, every non-zero element does have a multiplicative inverse. So the set of units is precisely all the elements except 0. Okay, let's see how the proof goes. Again, as we have proved in the previous theorem, the set of units of integers modulo P consists of residue classes that are represented by integers in the range from 1 to P, and GCD of A and P is supposed to be 1. Now, P is a prime number. That means a positive divisor of P is either 1 or P. Now, GCD of A and P is a positive divisor of P. So GCD of A and P is either 1 or P. Now, if A is an integer in this range, when A is positive integer is strictly less than P, it cannot be a multiple of P. So it cannot have P as a divisor. That means GCD of A and P cannot be P. It's a positive divisor of P, and it is not P. And therefore it is 1, because P has only 2 positive divisors When it's not p, then it should be 1. So this argument, which is crucial, a crucial property of prime numbers, says that if p is a prime number, every integer, every positive integer that's strictly less than p is co-prime with p. So if a is at least 1 strictly less than p, then GCD of a and p is 1. Okay, that means that this condition is redundant as long as a is strictly less than p, and of course p is not co-prime with p. That means ZP cross is the set of all the residue classes where a is in the range from 1 and strictly less than p, and that has p minus 1 elements. That shows that ZP cross is precisely the set of all the non-zero residue classes of Z sub p. That's an interesting property of integers modulo a prime number. Now let's try to understand Euler free function of powers of primes. Let's start with observing what it is for primes and the converse. So suppose n is an integer that at least 2, then we cannot have this property that the set of units is everything except zeros unless when n is prime. Let's try to understand this. We have already proved it, that when n is prime, we have this equality. Now we are showing the converse of that statement, at least for integers that are at least 2. So suppose that Zn cross is Z sub n minus 0. That means the Euler phi function of n is n minus 1. It has n minus 1 elements. Z sub n cross has n minus 1 elements, therefore phi of n is n minus 1, and that means the set of integers in the range from 1 to n that are co-prime with n should be n minus 1. It should have n minus 1 elements. That means what? Okay, of course n is not here because n is at least 2. N cannot be co-prime with n itself because GCD of n and n is n, and that's not 1. So that means having this equality implies that every integer that is at least 1 and is strictly less than n should be co-prime. Okay, so that's the definition of prime number. That means that every number that is strictly smaller than n and positive cannot be a divisor of n. And more than 1 cannot be a divisor of n, and that's a definition of prime number. Okay, so phi of n is n minus 1 if and only if n is a prime number, prime integer. Okay, so far we discussed that Euler phi function of n is n minus 1 precisely when n is a prime number. Now we want to understand what is phi of p to the k, where p is prime and k is a positive integer. By definition, phi of p to the k tells us how many integers we have in the range from 1 to p to the k, where GCD of a and p to the k is 1. So we are counting how many integers we have in the range. So how many integers we have in the range 1 to p to the k, so that GCD of a and p to power k is 1. That is the number we are interested in. In particular, we need to understand these numbers better, and the next claim is going to give us a concrete understanding of such an integer. It says that an integer a is co-prime with p to the k precisely when p doesn't divide it. And the crucial thing is that a is a prime number. If we use unique factorization into prime numbers, then this is an easy conclusion, because GCD of a and a power of p is not 1 implies that a and p to the k have a common divisor, but the only divisors of p to the k are multiples of p. From there, we deduce that a should have a prime factor p in it. But here we are not assuming the fact that we are not assuming uniqueness into prime factors, so we cannot simply use that result. Instead, we are going to use Euclid's lemma, which is essentially behind proof of unique factorization result. Okay, so let's try to show this statement that the greatest common divisor of a and a positive power of a prime number is 1 if and only if p doesn't divide a. Let's start with the easy side. We are going to assume that GCD of a and p to the k is 1. We want to show p doesn't divide a. We show the contrapositive of this statement. That means we are going to assume that p divides a. We want to show that GCD of a and p to the k is not 1. Because p divides a, of course, p would be a common divisor of a and p to power k, and therefore GCD, the greatest common divisor of a and p to the k, should be at least p, which means it cannot be 1. Okay, so this direction was rather easy as promised. Now let's go the other way around. And in order to show the other way around, that means we are going to assume that p doesn't divide a, and I want to show that GCD of a and p to power k is 1. And we are going to show this by induction on the power k. So we proceed by induction on k. The base of induction follows from more or less definition of prime numbers. So suppose p doesn't divide a. That means p is not a divisor of a. That means p cannot be a common divisor of a and p. So GCD of a and p is a positive divisor of p, which is not p. But remember, p is a prime number, so it has exactly 2 positive divisors. One of them is 1, the other one is p. Now, we are saying GCD of a and p is a positive divisor of p, which is not p. So it should be 1. Okay, that's exactly what we want to show. So if p doesn't divide a, then GCD of a and p is 1. Now I want to proceed and show the induction step, which means I'm going to assume that GCD of a and p to the k is 1. I want to show that GCD of a and p to power k plus 1 should be also 1. Okay, so let's call this GCD D, and I want to show that this D is 1. First thing that we notice is that by the base case, we already know GCD of a and p is 1. Now D is a divisor of a, therefore GCD of D and P is 1, because if they had something in common, then that would have been a common divisor of A and P as well. So GCD of D and P is 1, but D divides P to the K plus 1. So D divides, because it's a greatest common divisor of these two numbers, it is a divisor of P to power K plus 1, and D and P are co-prime. You see, D divides P times P to power K, but D and P are co-prime. That's exactly the setting of Euclid's lemma. So by Euclid's lemma, D should divide the other factor, because D and P are co-prime, D divides this product. We deduce that D divides P to power K. Therefore, D is a common divisor of P to power K and A. D also divides A, by the way. And D is positive because it's GCD, therefore it's positive. So D is a positive common divisor of A and P to the K, but greatest common divisor of A and P to the K is 1 by the induction hypothesis. So D is an integer which is positive and it is the most 1, therefore it is 1, and that's exactly what we wanted to show. So this shows that GCD of A and P to power K plus 1 is 1. That proves the induction step. And therefore, the claim follows, which means we showed GCD of A and P to power K is 1 precisely when P doesn't divide A. So The Euler phi function of p to the k tells us how many integers we have in this range that are co-prime with p to the k, but a and p to the k are co-prime precisely when p does not divide a. So we need to understand how many integers in this interval are not multiples of p. Instead, we count how many of them are multiples of p and then subtract it from the total number of integers that we have. So the number that we are interested in is the total number of integers in this interval. This notation we use to say the integers in this interval. So we count the number of integers in this interval, which is simply p to the k, and then subtract out the number of integers that we don't want, which means the number of integers that are multiples of p. Now, a is a multiple of p means a is p to power a prime, p times a prime for some other integer. Now, a is supposed to be in this interval from 1 to p to the k. Therefore, pa prime is in this interval. Now, I divide all the sides by p. P is a positive number, so it's fine. We are not changing the direction of inequalities. Therefore, a prime is supposed to be a positive integer, which means it is at least 1. And it's going to be at least p to the k divided by p, which is p to power k minus 1. A prime can be any integer in this range, and I multiply that integer by p, we get a multiple of p in the range that we are interested in. So this means the number of bad integers that we want to throw out is precisely p to power k minus 1. So altogether we get the Euler phi function of p to the k is p to power k minus p to power k minus 1. Now we end this video by summarizing algebraic properties of the set of units of integers modulo n. In particular, we show that this set is closed under multiplication. This type of property plays an important role in group theory and later in this course. So let's summarize basic properties of the set of units modulo integers and modulo n, the set of units of integers modulo n. So the first thing is that if I give you 2 units in the set of integers modulo n, their product is again a unit. The next property is associative, the fact that multiplication is an associative property. This we have already discussed. The next property is that with respect to multiplication, the set of units have a neutral element. This we have already discussed again. The only thing that we need to point out is that the coset, the residue class represented by 1 itself is a unit, meaning, so this itself is a unit, because when I multiply it by itself, I get the residue class of 1, and therefore this is a unit itself. And finally, every unit has an inverse. This is kind of a subtle point. By definition, of course, every unit has an inverse in the set of integers modulo n. But here we are pointing out that this element is not only an integer modulo n, it is a unit in the set of integers modulo n. So this a prime itself is a unit. And we discuss why this is the case. Again, we have already proved, as discussed, associativity of multiplication. We have pointed out existence of the neutral element with respect to multiplication. Now let's see why it is. Let's see why the set of units is closed under multiplication. So let's pick 2 units, and we need to show that the product is also a unit. What does it mean that something is a unit? It means that there is an element that I can multiply by and end up getting the residue class represented by 1. So because the residue class of A and residue class of B, both of them are units. There are residue classes, one of them represented by A prime, the other one represented by B prime, so that A, the residue class of A times the residue class of A prime is equal to the residue class of 1. Similarly, residue class of B times residue class of B prime is equal to the residue class of 1. Now, I want to find an element in Z sub n, and I want to multiply that element by the product of residue class of A times residue class of B and end up getting the residue class of 1. So I start with this, and I want to multiply it by something and end up getting a residue class of 1. My claim is that that something is nothing but product of these two residue classes. So it's residue class of B prime times residue class of A prime. Okay, let's multiply them. And I use the fact that this multiplication is associative, reorder the parentheses, and notice that the middle terms, when I multiply them, I end up getting the residue class of 1. Now, residue class of 1 is the neutral element of multiplication. That means when I multiply it by the residue class of A, I'm not changing it at all. So the first term times residue class of 1 gives me residue class of 1. And the way that we chose A prime, this product itself is the residue class of 1. So altogether, we get that the product of these two residue classes is still a unit. That means under multiplication, the set of units is closed. Let's finally discuss why every element has an inverse. Again, as we have pointed out earlier, knowing that the residue class of A is invertible, we deduce that it does have an inverse in the set of integers modulo n. But what I want to point out is that this itself is a unit. Now, what does it mean that this is the multiplicative inverse? It means that the residue class of A times the residue class of A prime is the residue class of 1. And of course, multiplication is commutative. We have already discussed this for the set of integers modulo n. Multiplication is commutative. I can flip the order. I get that residue class of A prime times residue class of A is again residue class of 1. These two equalities together imply that the residue class of A prime itself is a unit, and that's exactly what I claimed. So altogether, we showed these important properties of the set of units of integers modulo n. We showed that multiplication defines an operator on this set. We showed this operator is associative. We showed that it has a neutral element. This multiplication has a neutral element. That's residue class represented by 1. We showed every element has an inverse. Now, let's see from computational point of view how we can compute inverse, multiplicative inverse of a given element. So let's say I want to find a multiplicative inverse or the multiplicative inverse of the residue class of 20 modulo 47. Okay, so what does that mean? That means we need to find an integer x so that the residue class of 20 mod 47 times the residue class of x mod 47 is 1, the residue class of 1 mod 47. But this equality holds precisely when the following congruence relation holds. 20 times x is congruent to 1 mod 47. So we need to find a solution for this congruence relation. But what does this congruence relation mean? It means 20x minus 1 is an integer multiple of 47. So 20x minus 1 is 47 times y for some integer y. So we are looking for some integer solution of the following equation, negative 47y plus 20x equals 1. This type of equation we have discussed in the previous video, where we introduced we recall Euclid's algorithm. We showed that Euclid's algorithm gives us a way of finding integer solutions for equations of the form ax plus by equals to GCD of a and b. Notice that 47 and 20 are co-prime. So that's exactly the type of equation that can be answered using Euclid's algorithm. So let's see how we can proceed. By Euclid's algorithm, we are going to call the max of 47 and 2 to be a sub 0 and the mean to be a sub 1. And we start doing this reiterated divisions. So each time we divide, we capture the quotient, and the remainder would be the next term in our sequence. So we divide 47 by 20. We get the quotient of 2 and remainder of 7. Now, 7 would be our next term in this sequence, and q sub 1, our first quotient, would be 2. Now we divide 20 by 7. The next quotient would be 2. The next remainder would be 6. 6 would be our next term in this sequence. And we continue this process till we get to the remainder 0. So 7 divided by 6, we get quotient 1, remainder 1. And 6 divided by 1, we get quotient 6, remainder 0. And that's exactly where we stop. Now, we use this, observe this matrix multiplication. We said that this sequence of a sub i's, if I capture a sub I plus 1 and a sub I in this column form vector, a sub I over a sub I plus 1, a sub I in the first 1, 1 entry, and a sub I plus 1 in 1, 2 entry, then this matrix multiplication of 0, 1, 1, negative q sub I, 0, 1, 1, negative q sub I minus 1, and so on till we get to 0, 1, 1, negative q sub 1. Q sub i's are the quotients that appear in this Euclid's algorithm. As I multiply these 2 by 2 square matrices and finally multiply it by the first pair that I started with, a sub 0, a sub 1, we end up getting the final pair. In this case, the final pair is 1, 0. So we get the column 1, 0 by multiplying, and how many matrices? 2 by 2 matrices. Q sub 4 is the last quotient that we have. So we have to multiply these 2 by 2, these 4 2 by 2 matrices, and multiply the whole thing by this 2 by 2, by this 2 by 1 column vector 47, 20. We start by multiplying these 2 by 2 matrices from the right side. We multiply these 2, 0, 1 brings up the next, the second column to the first column. Then 1, negative 2 times this, we get negative 2. 1, negative 2 times this, we get 5. Again, 0, 1 brings the second column to the first one. And 1, negative 1 times this, we get 3. 1, negative 1 times this column, we get negative 7. And the thing that we need to notice is the following. This can help in certain computations. Sometimes we can avoid multiplication of large numbers by pointing out this. That this 0, 1 gives us 3, negative 7, and we don't care about the next row, because from this computation already we have the answer that we need. We already know that 1, 0 is equal to some matrix of the form 3, negative 7, and we don't care about the next row, times 47, 20, from which we deduce that 1 is 3 times 47, negative 7 times 20. Now, when I look at this equation mod 47, this disappears. I end up getting that 20, the residue class of 20 times residue class of 7 is the residue class of 1. And that's exactly what we wanted to end up getting. Now, we showed that this is a multiplicative inverse of the residue class of 20 mod 47. If we prefer a representative in the range from 0 to 46, of course, we can point out that the residue class of -7 is the same as the residue class of 40. So we get in the desired, a representative in the desired range. So altogether in this video, we've seen, we understood what elements of integers mod n have multiplicative inverse. Those are precisely the ones that are coprime with n. We understood that the number of elements in integers modulo n that are that have multiplicative inverse is precisely Euler phi function of n. We call them units. We showed that units under multiplication have the following properties. They are closed under multiplication, and therefore multiplication forms an operator on the set of units of integers modulo n. Multiplication have associative property. Multiplication has a neutral element in the set of units. Every unit has an inverse in the set of units. And these properties will be important when we discuss groups. And we showed and discussed how we can use Euclid's algorithm to find multiplicative inverse of an element in Z sub n. We learn about groups in the next video.